let's get started with today's material. So today we are covering what is called solid geometry. It's basically geometry in 3 dimensions. So we are now done with what is considered a standard planar geometry course. What's planar geometry?
Geometry.
It's geometry in a plane. So thus far we have limited ourselves to geometry in a plane. That's usually what most people mean when they're talking about Euclidean geometry is planar geometry. So we're done with that. Now moving on to what's often called solid geometry or space geometry is what this author calls it. Geometry in 3 dimensions. Now, first off, you're going to notice that the author hardly proves anything in the section. Why does he hardly prove anything in the section? Well, largely for 3 reasons. One, this is just meant to introduce you to, hey, this is also a field. We're done with the material proper to this course. So now this is just gravy. So we're not going to go through any of the proofs, partly because it's beyond this course to cover this material. Secondly, because nobody does 3-dimensional geometric proofs purely geometrically anymore. The way that the stuff in this section that we're about to introduce is typically proved is using calculus 3 and using calculus to prove these things, analytic geometry and then calculus on top of that. It's much easier. Geometry in 3 dimensions, we're going to see purely looking at the geometry, it can get messy fast. And we'll see that in some of the proofs we do here today. And then the final reason that he doesn't prove the things is the last thing I just said. The proofs are messy. The pictures get difficult. Because you remember, think how much we rely on pictures in our geometric proofs to give us our guiding intuition. You're going to find out today I am an atrocious artist. And so the pictures, it's just hard to get the picture there that makes it very clear for you to see it. So it might be more worthwhile if we had some sort of 3D generated stuff that we could look at to help see the picture, but we don't. So that's the 3rd reason. So the section is going to be pretty easy. You're going to see hardly anything gets proved. I'll prove stuff until I feel like it's getting messy. Then after that, we're just going to tell you that these are facts. Okay, so starting out, going from 3-dimensional geometry to 4-dimensional, or from 2-dimensional geometry to 3-dimensional geometry, it only takes 4 more postulates. So how many postulates do we have right now? Something like 17 or whatever. To extend our geometry to 3 dimensions only requires 4 more postulates. And they're going to be very similar to postulates that we've already seen in the past. So our first new postulate, what was our first postulate going all the way back?
There are at least 3 non-collinear points.
Perfect. And so our first postulate that we're going to be introducing today is that there's 4 non-coplanar points. So before, our initial geometry is that in a plane, I can find 3 points that don't all lie on the same line. Now our first postulate in 3-dimensional space is that there exists 4 points. So this point, this point, this point, and then my point right here, that don't all exist in the same plane. You can't construct one plane that goes through all those points. We're going to notice that going from 2 dimensions to 3 dimensions, now planes kind of act the way lines used to act. Kind of. Now to signify a point coming out of the board, I'm going to do a point and then put a circle around it like that. So this is a point sticking out of the board, and those 3 points are actually in the board. Okay? So there's 4 non-coplanar points. You cannot construct a plane that goes through all those points. What was our second postulate going all the way back?
You can draw a line through any 3 points.
Yeah, it was, our postulate was, given 2 points, there's a unique line containing those 2 points. So now, our second postulate that we're going to be introducing today is that 3 points, 3 non-collinear points, gives us a unique plane. So I take this point, and then this point out here in space. There's one and only one plane I can construct that slopes through all 3 of those points. So 2 points defines a line for us. 3 points, as long as they're not all on the same line, defines a plane for us. Go ahead.
Is that 3 points minimum or just 3 points?
It's 3 points defines a plane. It is identical to how 2 points gives us a line. Now when we say 2 points gives us a line, we do not mean that there's only 2 points on a line. We're saying pick any 2 points you want. There's one and only one line that contains those 2 points. So now in three-dimensional space, we're saying pick any 3 points you want, as long as they're not collinear. There's one and only one plane that goes through all 3 of those points.
And there is still like other points on the plane.
Yeah, the plane is still the plane that we've been working with this whole time.
Yeah.
So there's infinitely many points on the plane, just like there's infinitely many points in a line.
Is this like the same? I guess I'm just thinking back to the beginning of geometry when one of our postulates was that like when you have that a plane has 3 points. Is that like I feel like that's kind of roundabout. Like,
So that is like this one. So we started out, our first postulate is that there's 3 non-collinear points in a plane. Now our first postulate here is, and there's 3 non-coplanar points in space.
okay.
But yeah, still infinitely many lines of points on a plane, and still infinitely many points in a line. Just extending our geometry now so we're not stuck in this whiteboard. We're going to extend it out into space. Before we were stuck in one plane. Now our third postulate that we're introducing today, postulate 3, let's see, is this one that divides or is this one that says, sorry, let me just see it. Okay, so our next postulate here is, I don't know how to say it, we know these planes. What the postulate says is that the planes that we're talking about in space are the exact planes that we've been talking about this whole time.
Why does that?
So there's no difference between the plane we were talking about in planar geometry and now a plane in three-dimensional space.
Why does that have to be specified?
Because up until now, a plane wasn't one of our undefined terms. We are now introducing a new undefined term, plane.
I thought it was point line plane.
Nope. Before we just had points and lines. And we understood that the space we were in was a plane. That was just intuition to help guide us. But plane was not one of our undefined terms. So now we're introducing a plane, and we're saying that all the postulates that held for that space we were talking about prior in the class now apply to what we're calling planes in these things. And furthermore, it applies across planes. So if I take a right angle in one plane and a right angle in another plane, those 2 angles are still congruent, for example. So all the postulates hold in all these planes and across these planes. That's what our third postulate is saying. So the planes are behaving the way we know planes behave. And then finally, our last postulate, postulate 4. This one is similar to the lines, thinking about what lines do to the plane. If I take in this plane, right here, this wall going on forever, and I look at this line, then it divides the plane into 2 halves, so to speak, right? Well, in a similar way, if I pick any plane through space, imagine this wall now, except for I extend it to infinity that way, and it's a plane. I just divided the whole universe into 2 halves. Everything on this side of the wall and everything on that side of the wall. So the same way that lines divide a plane, planes divide space. So now let's read through the actual exact terminology he has for each of these, and hopefully it makes sense. So for our first postulate here, there is a set of points called space. Certain subsets of these points are called planes. There are at least 4 points that are not in any one plane. So we've got space, we got planes in space, and there's at least 4 non-coplanar points, is the way I'll say that.
Why is space not an undefined term? Like,
we technically would never need to make a reference to that. It's just we're going to give a name to the domain of individuals we're talking about. So you could put that as an undefined term if you wanted, but it's not really adding anything. In other words, putting on our first order logic hat, what we're saying is anytime we're talking about for all x, it's understood that for all x in whatever that thing is, space. That's all he's trying to get across. Obviously, he's not going to be that precise in his language. But, yeah. So, that's the first postulate. Any questions about the first postulate now? Try to give you intuition for it, and there's the exact terminology. Second postulate is there's exactly one plane containing any three non-collinear points. Pretty much exactly what we said. There's one and only one plane. Good? Next one. Each plane satisfies all the postulates for plane geometry. In particular, the line joining 2 points. Nope, can't read it all in one go. So each plane satisfies all the postulates of plane geometry. In particular, the line joining 2 points of a plane lies in that plane. Furthermore, the postulates of congruence of segments and angles apply whether or not the segments and angles are in the same plane. So our congruencies apply across planes. And then finally, our last one is each plane separates space, divides it in two. By this we mean that the set of points of space not on the plane consists of 2 subsets, called the sides of the plane, with the following properties. What does it mean for 2 points to be on opposite sides of a plane?
The line that connects them intersects the plane.
Yeah, their segment intersects the plane somewhere. It's exactly what we meant when we said 2 points are on opposite sides of this line. What did that mean? It meant that the segment AB intersected this at some point P. If you and I were on opposite sides of this wall, what would that mean? That would mean the segment connecting me to you intersects the wall at some point. If you and I are on the same side of the wall, then the segment from me to you does not intersect the wall. So same thing here. If 2 points are in the same subset, then the segment joining them does not meet the plane. But if 2 points are in different subsets, the segment joining them does intersect the plane. Now keep in mind, the plane really divides space into 3 sets. There's the points on one side, the points on the other side, and then the points actually on the plane.
Yeah.
So it's not that every point has to show up on one side or the other, it's every point not on the plane shows up on one side or the other. Okay, so those are our only 4 new postulates. That's it. And now we're going to see what we can start proving with just these 4 new postulates. Any questions so far? All right, let's get started, get a feel for how these types of proofs go. Where's theorem 14.1? Okay. Zoom in on some so that you can read it. A little too much. Okay. If a line L does not lie in a plane pi, typically you use Greek letters to make reference to planes. So from here on out, anytime you see a lowercase Greek letter, we're talking about a plane.
It's really kind of confusing.
Well, we use capital letters to talk about points. We use lowercase letters to talk about lines. And so what do you use to talk about planes? Greek letters.
Okay.
So just trying to keep it quick. All right, so let's see. So I've got some plane here. Now, remember, I'm only drawing a portion of the plane. The plane, it goes to infinity. All right? So here's some plane in space, and I've got some line. Comes down, here's the point P, and then it intersects the plane at that point. And then you can see it from there on out. Try and make the picture look somewhat decent. Here's L. This is the plane pi. So if L does not lie in a plane pi and has at least one point in pi, so my line L, it does not lie completely in pi. It's not necessarily perpendicular to it, that's just my drawing. Don't read too much into the drawing. But it does intersect at one point, then L and pi have exactly one point in common. In other words, if a line is not in a plane and it intersects the plane, it can only intersect it at one point. It cannot intersect it at 2 points. Let's think through the logic of that. Why is it that L can't intersect it at P and some other point P prime? Why does that get us in trouble?
Because in the line containing P and P prime would intersect L twice.
Notice that there is, going back all the way to our earliest postulates, 2 points give us how many lines?
1.
1 and only 1. So there's one and only one line, and that line is in pi, call it L prime, that contains those 2 points. If L also contains those 2 points, then it is at one and only one line, L prime. But L prime's in pi. So if a line contains 2 points in a plane, the line has to lie completely in that plane. You see the logic there? You want to write out the proof, or you think you got it?
Makes sense.
Think you got it? All right, let's try another one. That jumped a lot because I got to scroll to the side. Okay, theorem 4.2. And once again, you're going to know this author doesn't bother proving any of these things, so don't go to the book looking for proofs. You're not going to find them.
Right.
All right, let's try another one. Let me say something. There's a lot of proofs in this section, but the homework is going to be very simple. And all the author really wanted to do is to help you get intuition for what these proofs are saying. So he wasn't trying to get you to understand how to prove it. He just wanted you to know what is the proof actually saying. So there'll come a point where I'm just going to focus on that. But let's prove a couple just to get a feel for using these things. Okay, next one. There's a unique plane containing a given line and a point not on the line. All right, so I've got a line. Here's L. And I've got a point not on the line, P. Now imagine this line hovering in space, no way attached to this board, okay? So here's this point hovering in space. Here's this line hovering in space. Now the plane that comes like this does not contain that line and that point. There's one and only one plane that contains that line and that point. And that's perfectly the one that lies at the surface of this chalkboard. That's the only plane that contains both that line and that point. No other plane you can come up with contains that line and that point. You with me?
Yeah.
If we were talking about the line and this point at the end of my chalk here, what plane would that be? That would be the plane that cuts through here and goes into the chalkboard like that. Right?
Yeah.
Okay. So let's check what we're proving. There's a unique plane containing a line and a given point. So first off, how do I know there is a plane containing these?
You could find 3 points on the line.
Yeah, it would be postulate 2, but first, every line contains
2 points.
at least 2 points.
Oh, yeah.
So we'll call them A and B. Okay, so I've got A, B, and P. How many planes are there containing A, B, and P?
1.
One and only one. How do I know that?
Postulate.
That's postulate 2 here. Right?
Yeah.
Now, postulate 2 only applies if these 3 points are non-coplanar. But it was given to us that P is a point not on the line. So I've got a line and a point not on the line. So A, B, and P are for sure non-collinear points. So there's one and only one plane that contains those. Oh, so there is one. How do I know that there's only one plane?
Because that's what the postulate says, isn't it?
Again, postulate 3 says there is a unique plane containing any given 3 points. So the plane that contains those 3 points is the only plane that contains those 3 points. So there's one and there's only one. Good? Need to see it written out, or you think you got it?
That makes sense.
All right, let's try 14.3. There are infinitely many planes containing a given line. All right, let's try that one. Let's actually write this one out, just so we write out at least one proof. Okay? So what theorem are we on? 14.3. We're going to prove that there are infinitely many planes containing a line. Okay, so 1, let L be a line. So any line in space we want. Let's close the projector for a bit just so I have some scribble space to draw a picture. So over here, so far what do we have? We just have a line L, right? I'm trying to prove that there's infinitely many planes containing line L. Now first off, let's try and get intuition for that. Need something kind of just long like this. Okay. So first off, imagine the plane that slants from that line down through here. There's one plane that contains this line. If I lift it, now imagine the plane that goes through here in that line. There's another plane. Here's another one. Here's another one. Here's another one. And so I can construct infinitely many planes that go through that line. It's like if I had a ramp that terminated right here, how many angles can I potentially make that ramp on? Infinitely many. Feel like you got intuition for exactly what this is saying?
Yeah.
Okay, and with that, let's prove it. Okay, so I've got L here. All right. I'm trying to prove that there's infinitely many. So first off, let's find a plane that goes through it. Now, what am I guaranteed by my first postulate?
There's 4 non-coplanar.
There's 4 non-coplanar points. So I know let's see, let L be a line. Let's just name 2 points on L really quick. Comma. And let A be some point in L and B be some point in L. Just to name 2 points on the line so far. Good so far? Now, by this postulate, I'm guaranteed that there's 4 non-coplanar points. So not postulate 4, postulate 1. By 1, comma, there exists 2 other points. There exist points C and D such that A, B, C, and D are non-coplanar. So I'm guaranteed that there's some other point out there. Here's C. We'll say that C is in that same plane. And then D here now has to come out of the whiteboard. So D is somehow sticking out of the whiteboard. So segment CD slants out of the whiteboard like this. It slants up out of the whiteboard. Just to make sure we're understanding the picture, does the line L and the line through CD intersect? No, because C comes up above it. It slants up out of the whiteboard. So those 2 lines do not intersect. Just trying to make sure you're understanding my picture. Good so far? Okay. 3, let M through CD. So now M is going to be the line that comes out of the whiteboard here. And then at C, this is where it goes into the whiteboard. So it's actually intersecting into the whiteboard at that point, and it comes out, right? So this is line M. Good so far? Okay, what are we trying to do? I'm trying to prove that there's an infinite number of planes that go through A and B. Right? So, 4. Then, for any point P in M, comma, there exists a plane, we'll just call it pi, there exists pi containing A, B, and P. So now pick any point P in this line you want, doesn't matter which point. And we know, since these 3 points are non-collinear, there's one and only one plane containing all 3 of those points. Go ahead.
Is using pi as a name for a plane, like, standard?
Yes. I will always, as my first variable, just like we always start naming lines with L, I will always start by naming my planes with pi.
That won't get confusing.
Is that
How?
how? Isn't it like a number? You know?
Isn't that a letter? What do you mean it's a point? You just get used to these things. Pi is a very common variable name. So pi for planes, pi for permutations is another way it comes up often.
After pi, what would be the next? Like,
Sigma is a pretty common one. So we'll just, we can make up whatever symbols we want, but there it is so far. Okay, so now for any point P on this line, then there exists a unique plane containing those 3 points, right?
Yeah.
Okay, how many points are there on M?
Infinitely many.
There's infinitely many points on a line. We already know that, right?
Yeah.
So there's infinitely many planes that I can construct through the points A and B. I pick A, B, and then some point on this line. I just keep picking different points on this line. Every time I pick another point on this line, those 3 points, A, B, and that point,
make a plane.
give me a plane. 5. Then L is always in pi. The line is always in pi. since the plane contains A and B,
Right.
right? If my plane contains the points A and B, it has to contain all of L.
Right. We proved that.
Yeah, we already proved that one as, I think, our first theorem. So, then L is in pi, since A and B are in pi. Okay, so we just found infinitely many planes that contain the line L. Now there's one little technicality that we might want to account for. I showed that pick any 3 points you want, that gives you a plane, and I can do that infinitely many times. How do I know they keep giving me different planes?
Because they're
Maybe it keeps resulting in the same plane every time. Or maybe I'm just cycling through a trillion different planes, and it ends up coming back and cycling on itself.
Doesn't that go to postulate 2? It gives you a unique plane for every 3 points, and we know those aren't the same points on it.
Yeah, different points for different planes, right?
Yeah.
No.
Oh.
Because imagine what you're saying. So think about it. Here's A, here's B, and then here's P. There's a unique plane containing those 3 points, but it's also the same plane containing these 3 points. So there is one and only one plane containing those 3 points, but that doesn't mean if you didn't pick a different point, you didn't end up getting the exact same plane.
Isn't it one of the earlier theorems then that was saying that there's only one point on a line that, so on a line that's not coplanar to whatever plane, there is only one point on that line that intersects with that plane?
What's the first one on theorem 14?
Perfect. Exactly what he just said. One of the first things we proved is that a line intersects a plane at a single point. If M intersects the plane through ABP at P, it can't do it at some later P.
Okay.
Make sense? The point is, these theorems are being given to us in a logical order. And you notice how we're making reference to our previous theorems. How do I know that there was only one, or that it gave us a unique plane? I think that was theorem, the first one we did. How do I know that we're not secretly cycling through the same planes over and over again? What he just said, what was that? The second or the third one that we did? Whichever one it was. Good? So, I don't know, put 6 here. By theorem, whichever one it was, we know that each P in pi, or each P in N gives us a unique plane. And then you're done. Any questions so far? Not too bad, right?
Nope.
Okay. Which one did we do?
We just did 14.3.
14.3, so 14.4. There's a unique plane containing 2 intersecting lines. So now, pick any 2 intersecting lines we want, L and M. We need to prove that there's one and only one plane containing those 2 lines.
By intersecting lines, do they mean lines that intersect on the same plane?
By intersecting lines, they mean lines that have a point P in common. Imagine I pulled a string from one corner of this classroom to the other, down, across like that, and I pulled another string like this. If the classroom was perfectly rectangular, those 2 strings would touch right at the middle point. Those 2 strings touching are like 2 intersecting lines. That would mean that there's one and only one plane I could construct that slanted perfectly with those 2 strings. If you're used to construction, often you pull strings to help you get things level, like even a sheet of plywood, something like that. It's the exact same concept here.
okay.
Okay.
So, I need to prove that if 2 lines intersect, they have at least one point in common, no matter how they are scattered through space. If those 2 lines intersect, then there's one and only one plane containing those 2 intersecting lines. Good? So these 2 lines, let's say they intersect at P. How do I know that there's a plane containing those lines? First off, what do I know about lines?
They have 2 points.
They have at least 2 points. I've already got 1 point on L. So there must be some other point on L, call it A. I've got 1 point on M. So there must be some other point on M, call it B.
Oh, yeah, and there's 3 points.
And that gives us 3 points. And there's one and only one plane containing these 3 points, since they're non-collinear points. So there's one and only one plane pi I can construct that contains this point, and this point. But if pi contains P and B, it must contain all of M.
And if it
Because 2 points give
if
us
it contains A and P, it must contain all of L.
exactly same exact thinking. So if you contain 2 points of the line, if a plane contains 2 points of the line, it has to contain the whole line. So since it has those 2 points, it has all of M. Since it has those 2 points, it has all of L. Now that make sense? Pretty straightforward proofs, right? All right, theorem 14-5. If two distinct planes have at least 1 point in common, they have precisely a line in common. Let me open the projector just so you can see his picture really quick. Pictures often help. So looking at that picture down in the bottom right, we've got 1 point in space, pi 1, slanting this way. 1 point in space, pi sub 2, slanting that way. Right? Now what we know is that these two planes intersect at some point P. What we need to prove is that then they actually intersect at a line and not just a point. So when two planes intersect, it's impossible for 2 planes to intersect at just a point. If 2 planes intersect, their intersection is an entire line. It's not just a point. You with me? Okay. So, let's try out that proof. So for my picture, we're going to draw out, here's one of our planes, and it's just going to be the whiteboard. Or maybe we'll draw a piece of the whiteboard. Here's pi 1. And to save me any drawing abilities, we're going to say pi 2 is a plane that cuts right in like that.
Okay.
Right?
Alright.
Coming right out at you. Hurts a little. That's pi 2.
Okay.
And I know that pi 2 intersects pi 1 at least a point P. Right?
Yeah.
Okay. What do I know about planes?
They have at least 3 points.
I know they have at least 3 points in them. Okay.
They divide the space.
I have 3 non-coplanar points.
They have 4 non-coplanar points.
Or sorry, I have 3 non-collinear points in a plane.
Wow.
You can say that. Wouldn't it be worth it to try and draw it? I think I'll make a mess. Okay. So I do know that. I know that there's 4 non-coplanar points in space. Okay. What else do I know about planes? There's one of those postulates we haven't used yet.
They divide the space.
They divide the space. And so a plane divides all of space. So pi 2 here divides all of space.
Oh, I see.
Right?
Yeah.
So that means every point on pi 1 is either on one side of pi 2, on the other side of pi 2, or on pi 2. Right?
Yeah.
Okay. So let's think that through a little bit. So I know that. Well, so what does that give us?
That there's a,
Since it divides the space, it divides pi 1. So either pi 1, all its points are on one side, or pi 1 intersects pi 2 somewhere. We already know pi 1 intersects pi 2 somewhere.
right.
So I already know that there must be a point in pi 1 over here, and another point in pi 2 over here,
That the line connecting them intersects.
such that the segment intersects there. Okay? What am I trying to get?
You're trying to get that the intersection of pi 2 and pi 1 is a line.
Yeah. How do I know that it's going to be a line here? Think it back to our earliest postulates of a line.
You have to show those 2 points.
Only
2 points there.
contains 2
intersection.
points.
What else do we already know about lines?
They have 2 points in them.
They have 2 points in them. That's one thing we know. What do we know about lines that's a lot like this thing?
They divide the plane into 2
Oh
sides.
yeah, so there's 2
Lines
sides.
divide planes. So if a plane is divided, it's divided by a line. So I know that this plane divides this plane. So what does it divide it by?
A line.
A line. And what's dividing it by is their intersection. So their intersection must be a line.
Right.
Because their intersection divides pi 1. Does that make sense?
Yeah.
So it's just reusing that same postulate that we already do for planes. Go ahead.
What if the planes look like this? where like they intersect at that one point, but they don't. Like,
The planes go on forever. You're drawing pictures of a plane. So you're drawing planes like this, where this one touches this one,
right.
but they go on forever. And so you have to keep extending however those things are touching into each other. And so if you keep extending this side and extending that side, then they're going to meet, and keep on meeting.
Okay.
So remember, planes are infinite, so to speak. Any other questions on that? Okay. Next one. Okay, our next one is a definition. And it's going to be the definition of a dihedral angle. It's going to be very similar to our definition of just an angle. Thinking back to regular geometry, what was an angle? What's an angle? What's the geometric figure of an angle? It's two rays
Intersecting at one point.
that start at one point,
Yeah.
and they go off like that. And that gives you an angle.
Yes.
Right? A ray is kind of like a half line. Right?
Yeah.
We take where two lines intersect, and then we pick half of each of them. And that gives us an angle.
Yeah.
Right? Similar concept now for a plane. So take two planes, pi 1 and pi 2, that intersect each other. And they're going to intersect here at this line L. Then the half plane and the half plane are going to give us what we call a dihedral angle. Rather than using two half lines, we're using two half planes. And so he's calling pi 1 plus this half of pi 1. So pi 1 is this whole plane. And he's using pi 1 plus to refer to the half starting from L. And pi 2 plus to refer to that half of that plane. Go ahead.
What does dihedral mean?
So the di there means that it's going to be composed of two. And then the hedral is just letting us know that now we're in spatial. We're in space. So a dihedral angle is going to be like our simplest version of an angle that we now get in this space.
Okay.
Because the angle between two shapes is no longer well defined. What is the angle that those two walls meet at? When you look at those two walls, you naturally want to say that they meet at a 90-degree angle. Right?
Yeah.
But you're just assuming I'm going to make some perpendicular cut. Why are you measuring the angle that way? Why is it 180 degrees if you go down the line? Or if you slant the way you measure just a little bit, it's going to be really close to 180. Why are you saying it's perfectly 90 degrees? And it's because you're assuming this type of interpretation as to what we mean by the angle. There's a bunch of ways I could draw one of these types of angles in that corner.
Yeah.
And so we need something more spatial to talk about our angles now in space. So a dihedral angle is going to be the simplest version of an angle that we could talk about in space. It's where two planes meet, and here's the angle. It's the way the planes shoot off. Make sense so far? We can read his exact definition now. If two planes, pi 1 and pi 2, intersect at a line, L, let pi 1 plus and pi 2 plus be half planes of pi 1 and pi 2. Half planes include L, the same way that rays included the vertices. Okay. The set of all points in pi 1 plus and pi 2 plus is called a dihedral angle. The L is called the edge. Rather than the vertex of this angle, we now have the edge of these angles. Functions just like the vertex. The line L is the edge. Pi 1 plus 2 are called the faces of the dihedral angle. So now, rather than talk about the sides of an angle, we talk about the faces of the angle. Make sense? Just terminology. Now, when we went back and we had two angles here, so we usually call this ray R1 on some line L1, and we call this ray R2 on some line L2. What was the interior of the angle?
It was all the points that were
All
on the
the
same side of
points.
L1 and L2.
It was all the points on the same side of L1 as R2,
R2.
and all the points on the same side of L2 as R1. and that gave me these points as my interior. Think about the interior angle now of the corner of our classroom here. Using the two walls to create a dihedral angle, what does it mean to be inside that angle?
You're inside the two, like, the...
Imagine these two walls went on forever. It would mean that we're on the same side of that wall as this half of this wall, and we're on the same side of this wall as that half of that wall.
Yeah.
So that's exactly what it's going to be. What's going to be the interior now of these angles? It's going to be all the points on the same side of pi 1. Remember, pi 1 is this whole plane. It's all the points on the same side of pi 1 as pi 2 plus, and all the points on the same side of pi 2 as pi 1 plus. Is that half plane?
Okay.
So it's almost the exact same definition. That make sense?
Okay.
Okay. All right, next definition is what it means for a line to be perpendicular to a plane. So imagine the line now that goes perfectly into this whiteboard. Perpendicularly. So a line that shoots directly out of the whiteboard like this. You with me? What is its relationship to this line in the whiteboard? If it goes through it right here, here's our point of intersection. Our line goes through it. It's going to be perpendicular to that line. And what about to this line? Imagining it went through the same point.
It would also be perpendicular?
It's also going to be perpendicular to that line and to this line. Right? And so, if a line is perpendicular to the plane, it's going to be perpendicular to every line that goes through that point in the plane. Because we already know what it means for two lines to be perpendicular. So we need to define being perpendicular to the plane in terms of being perpendicular to a line. Make sense?
Yeah.
So that's exactly what our definition is going to be. So, definition 14.3 now says, a line L is perpendicular to a plane pi if L intersects pi at a point P, so it has to intersect it, and is perpendicular to every line in pi that passes through P. Oh, he's got a picture here for us. So here is L, here's pi. L has to be perpendicular to every single line in pi that passes through the point P. Pretty straightforward definition?
Oh, okay. Yeah, that actually makes some sense.
Okay, so let's see where our next theorem is. If a line L is perpendicular to two intersecting lines, then it's perpendicular to the plane containing those lines. Alright, so try and draw this. Here's our plane. There's pi. And I've got M and N here. And I know that L we'll call that the point P. I know that L is perpendicular to both these lines. You with me?
Yeah.
I'm trying to prove that L is perpendicular to pi. What does it mean for a line to be perpendicular to a plane at a point? It means it's perpendicular to every line in the plane that passes through that point. So what I need to prove is that for any other line we construct through that point, O, in the plane, L is also perpendicular to O.
Isn't that given by the definition?
What we are trying to prove is that if L is perpendicular to M and N, then it's perpendicular to pi.
Oh, I see. Okay.
What's the definition of L being perpendicular to pi? It's perpendicular to every line through P. So I know L is perpendicular to this line. I know it's perpendicular to that line. I need to prove it's also perpendicular to this line. And then we're done.
Okay. Got it.
Let me put my N over here just so that we have all our line names on the same side. Okay. Let us try and think about how we would do this. So I'm trying to show that L is perpendicular to O. You with me?
Yeah.
And so the way I'm going to try to do this, so I'm going to pick on L. I'm going to pick some point. I'll call it A up here. And some other point down here. Call it A prime. And I'm going to pick it so that AP is congruent to A prime P. With me? Now I'm going to pick some other point in O, call it B. And what I am trying to show, so I know that B is some random point in O. What are we trying to show? Essentially what we're trying to prove is that AB is congruent to A prime B. If I can show the distance from A to B is the same as the distance from A prime to B, then what does that mean? Let me draw the plane for a second just containing L and O. So we're going to scribble that. We'll do it over here so we can keep writing down here. Here's a plane just containing L and O. So here's L. Here's O. Here's A. Here's P. And here's A prime.
Okay.
I'm sorry, I just disturbed you, but it was nice to hear from you this morning. Do we have anybody on today?
We've got everyone today.
I love it. Good job. Okay. Thank you.
Thank
Would
you.
it mean that angle APB is congruent to angle A prime B PB, which means that it's...
Well, hold on for a second. So let's finish drawing our picture, and here's a point B. So this is just me drawing the plane that contains L and O. Now, we are trying to argue that that is a right angle, that they're perpendicular to each other, right? Which, if I can show that AB is congruent to A prime B prime, then we already know that those are right angles. Because all the points that lie exactly equidistant from A and A prime are the perpendicular bisector of the segment A prime. So all the points equidistant from A and A prime lie on its perpendicular bisector.
Yeah.
So if I can show AB is congruent to A prime B, then I show that O is perpendicular to L. So what I'm trying to prove ultimately is that AB is congruent to A prime B. That's what we're trying to get after. With me? Okay. So, how on earth am I going to do this? Might have been premature with our B here.
Can we use the fact that they're right angles, or is that what we're trying to do?
Well, these ones have right angles, so I know that one's a right angle and down to this one is a right angle. So I've got to use that information, construct triangles. Okay, here's actually what I'm going to do. I'm going to start by picking C and D. So C and M, D and N. So that PD is congruent to PC. So we won't grab our point O yet. So I've got D in N, and I've got C in M, such that PD is congruent to PC. And then I'm going to let B in O such that O is between CBD. Such that O is a point between them. Okay, so we still are trying to prove that AB is congruent to A prime B, and we'd be done. But now I know that this segment right here is congruent in length to this segment. And that B lies in between them. Okay, I kind of chose a bad way to draw this picture, unfortunately. I should have drawn it so all these points are sticking out this way, and then I think we can see it better. So I'm going to redraw our exact same picture, orienting it a little bit differently. So maybe a bigger plane so that we have more space to draw. Here's our point P. I'm going to want my lines. We'll have a line coming like this, a line coming like this, and a line coming like this. If we're reorienting it, this will be our line M, this will be our line O, and this will be our line N. So kind of just twisting that picture. That's our point P. Here is L, and it goes through the plane right there. C is right here, D is right here, and B is somewhere in between them right here. A is up here, and then A prime, oh, that was the same line. A prime is somewhere down here. Okay, you see how I just rotated my picture?
Yes.
Okay, so once again, I know that this is congruent to this.
So it's an isosceles triangle, PCD.
PCD is isosceles, but now, hurt your brain, look at triangle AC. Let's see. Oh, is that the one I want?
ACP?
ACP. Yeah.
ACD.
ACD. Oh, yeah.
ACD is.
ACD.
But I was thinking it
CD. Well, B is line is a.
Let's see.
C and D. ACD would contain B then.
Oh yeah, and then PC
Let's
plus AP
think.
is equivalent to PD plus AP.
In order for me to show
Because AP is the same. So it's still an isosceles.
A, P, B, that side.
The real question would, if you know that PC and PD are congruent and AP and AP are congruent, does that mean that AC and AD are congruent because the ratio has to stay the same?
We can't jump to that. So hard to see the triangles in three-dimensional space. Because let's see, I want to say that AB is congruent to A prime B. I'd be able to say that, kind of reverse my thinking here. How would I know that is the case? I would know that that is the case if triangle APB were congruent to triangle A prime PB. So look at that triangle. AP coming out to B, and then A prime P coming out to B. You see those two triangles sticking out at you? APB gives us a triangle sticking out of us. Its base is a long line O. And then A prime PB, that would give us a triangle. If I could show that those two are congruent, and I would be able to say that if I could say something about angle, I could get there if I could get that angle ABP were congruent to angle A prime BP. That would help me get there, would help me get there. So APB, I need that now to somehow be on another triangle as well. Oh, I'm missing something obvious. Let's see if this is one the author does. Okay, this is one that the author does. Let's piggyback on his picture. Yeah. Again, getting these pictures right, it's such a big part of the proof, which is why, again, we all use analytic geometry to do it, because then you're just using equations to describe things. And talking about where equations intersect is just doing the math. Okay, So let's see how he set up his. Here's his picture. Let's just zoom in on it a little bit so that we can all see it. So his picture's right here. So he started out with L1 and L2 in the plane, and he picked some other line M in the plane. He did exactly what we did. He marked off a point A up here so that PA is the same as PA prime. Those are the same distance. And then he picks two other points B and C on L2, and he let Q be the point between them. Okay, so we had a B here. He's using Q. So ultimately, using his picture, we are trying to prove that AQ is congruent to A prime Q. If we can get there, we're good. Right? Okay, and now let us think how we could get that using a better picture here.
And then APB and APC are right angles.
So yes, this is a right angle, this is a right angle. And since I know that those are right angles, also it was chosen so that the distance here is the same as the distance here. And so I can see that triangle APC is congruent to triangle APB, if I wanted. But if I can show AQ is congruent to A prime Q, we're done. I'm trying to see the triangle I want to use with that.
Aren't you trying to use triangle ABC and A prime B, C prime?
So if we use triangle ABC, oh,
We
perfect.
can do APQ.
Because Q is in between B and C.
APQ? We don't want to use APQ. So-
No. Okay, yeah.
I think what he's saying is a good idea. So let's look at triangle here, ABC for a second. You see that triangle?
Yeah.
What do I know about that triangle?
Bisecting side there. Or no.
It's going to be an isosceles triangle.
That's an isosceles.
How do I know it's an isosceles triangle? Since B lies on L1 and C lies on L2, and that distance is the same as that distance, and they're the same height, and those are right angles, those two triangles are congruent to each other. And so I know that the length of that side is the same as the length of that side. So it's an isosceles triangle.
Right.
And so the base angle of ABC here is congruent to the base angle of that there.
Right.
Oh, but we need to flip it down and compare it to the picture down here, because I'm trying to say that this is the same as this. So I'm comparing congruency the wrong way. Let me compare congruency, this time looking at triangle ABQ to A, or compared to A prime BQ. Or start with ABC and A prime BC. There we go. Okay, so all the arguments I said before hold, so that this is in fact an isosceles triangle. That angle is congruent to that angle. But now look at the triangle down here using A prime BC. It's going to be congruent to this triangle up here. How do I know that? Well, I know the distance from A to B is the same as the distance from A prime to B. How do I know that? Because L and L1 are perpendicular. And so, if I looked at the plane just containing L and L1, L1 lies on the perpendicular bisector through A and A prime. You with me? And so that gives me that this triangle down here, A prime BC is congruent to ABC. So that's where we're trying to get. Let's go through our thinking here a little bit more for a second. I know that ABC, triangle ABC, is congruent to triangle A prime BC, which gives me that these two angles are congruent to each other, which gives me that triangle ABQ is congruent to A prime BQ. You see that? We can say ABC is congruent to A prime BC. How do we make that argument? We could have used side, side, side here. Let's erase and recapture how I see that those two triangles are the same. So looking at just these two triangles, ABC and A prime BC, notice that this distance is the same as this distance. Why? Because L1 is perpendicular to L. And so L1 lies on the perpendicular bisector through A and A prime. So that's how I got that this side is congruent to this side.
Gotcha, okay.
I got that this side is congruent to this side for the same reasoning. And in fact, it's going to be the same big as that one because of how we chose those points. Although, come to think of it, I could pick C to be any point now. So even if they were different points, it doesn't matter. And then finally, BC is the exact same for both of them.
Yeah.
Okay, so that gives me that triangle ABC is congruent to triangle A prime BC.
Yep.
Now that I know that those are congruent, what that gives me is that angle ABQ is congruent to A prime BQ. Because angle ABQ is angle ABC. ABC is congruent to angle A prime BC, but that is the same thing as angle Q is congruent to angle A prime BQ. You see how those are the exact same angles?
Yeah.
ABC is the same thing as ABQ in terms of the angle. It's this angle.
Yep.
And then once again, A prime BQ is this angle. You with me?
Could we use supplements?
Well, we've got it now.
Oh yeah, but I was wondering if we could.
Use supplements.
Like, we're kind of.
They don't make straight angles, so those aren't supplements to each other.
Oh yeah, you're right.
Okay, and now finally looking at triangle ABQ and A prime BQ. Those two are congruent now. How do I know that? How do I know triangle ABQ is congruent to triangle A prime BQ? How do I know ABQ is congruent to A prime BQ? Side angle side. These sides we already talked about are the same length. Don't know why I erased it. That angle is the same as that angle. Now that side's the same as that side. And so I got that those triangles are congruent to each other.
The
Which-
AQ is congruent to A prime Q.
Which gives me that AQ is congruent to, we use the first and the third, so the first and the third. A prime Q. These ones were congruent by side angle side. Okay, there we go. So the logic to that, honestly, not that bad. The hard part was seeing the triangles. Right? And so the right picture helps so much with this, and the fact that I was drawing my picture messy made it hard to see. Then you go to a nice author picture. It's the exact same picture we were using, but it just makes it so much easier to see everything.
Yeah.
So that's why these proofs are such a pain. It's not that the logic is horrendous, the logic not that bad. It's just seeing what on earth you're talking about is a pain. So we'll probably stop proving these now as we go and just help establish intuition for what each one is saying. You will not be required to do anything remotely that difficult in your homework. This is going to be a very easy homework section if you're worried about that. It's going to be things like restate this postulate in your own words type stuff. Or go get some scissors and a cardboard and cut it out and make your own 6-sided dice or something.
Okay, we're not doing that.
Yeah, I want to see these dice that you guys make out of cardboard.
Already have that.
Kindergarten was a long time ago. Let's see if you still got it. That's a joke. Don't bring me any cardboard renderings. Don't. I'd have to pretend to be impressed. You'd be embarrassed by how it looked. It just wouldn't be good.
Let's go hang it on the fridge.
It's not a bad idea. Get a fridge door in my classroom that I
Do
can
you
stick
want-
stuff on.
You want us to do the constructions and stuff?
I doubt they'll have you do any constructions. Your homework for this section is going to be pretty easy. Let's read one of the homework problems. State two theorems analogous to theorems 14.7 and 14.8 concerning the existence of lines perpendicular to planes.
Yeah, then let's prove the theorems that you say in
Analogous?
exercise 1.
Prove the theorems that you state in exercise 1. Well, we'll see whatever those are.
That is exactly perpendicular left to a line.
Alright, next one, 14.8. There's exactly one plane perpendicular to a line containing a point not on the line. Okay, let's make sense of what that one's saying. I've got a line. What's it saying? Not on the line? There's exactly one plane perpendicular to a line
Did we do 14.7?
and containing a point not on the line. No, I think we skipped 14.7. there's exactly one plane perpendicular to a line at a point on the line. Okay, so first off, 14.7. So here's P, a point on the line. What they're saying is that there's one and only one plane I can construct perpendicular to the line L going through point P. You with me so far? Okay, so how do I know that there is a line perpendicular to L through point P?
By one of our postulates from, or one of our theorems, wasn't it?
I think there is a theory.
How could we do it? We want to prove that there is some plane I can find in existence perpendicular to this line that goes through that point P.
Well, there's infinitely unique planes, so one of them has got to be.
You have to consider the plane that the line lies in, don't you?
Not that L lies in. The plane that's perpendicular to it is getting cut into the whiteboard like this.
Right.
But we can first talk about the L, the line L1, that is perpendicular to L. We know how to do that.
Then
Oh yeah, we just
There's
proved.
at least one line out there that looks like that.
just find a couple points in L1.
We just proved that there is a plane. I feel like because we proved that there were on a plane there were.
So we're guaranteed that there are the planes. How do we find the ones that are perpendicular? So now I need the plane that goes through L1 perpendicular to L2. And it's going to be very similar to now the construction that we did before. How am I going to find a point, the third point I want to use for this plane?
I'm gonna put it on the line.
It's what is the property it's going to have? It's going to have the property that pick any 2 points on L here. You're basically re-going through the construction of the previous proof. Pick A and A prime. Now what are we looking for? We're looking for a point equidistant for both of them.
If those are congruent segments, right?
So all I need now is 2 lines, 1 through A and A prime that intersect. Or, well, how's an easier way to say that? Yeah, how do we talk about the existence of that line, of that point?
You mean P?
Because we need to find some other point out here. No, we need one more point that lies in that plane. And I know that's going to have the property of being equidistant from A and A prime.
Well,
Yeah, you
each
can
line
start that
has 2 points, so you just put another point that's equidistant. It has infinitely many points, and it has 2.
How do I find the one that's equidistant?
You just find it. You find it.
You just find it.
You can find on L1K.
So
Yeah, on
2 of my
L1,
points are
that's
coming off of L1, that's fine. Now I got to get a third point not on L1, but I need it to be perpendicular to L1. Or not perpendicular to L1. I just need it to be equidistant from A and A prime.
Can you construct 2 planes?
I guess, yeah, that would be the way to do it. So pick some point here, call it B. Construct the point through A, B, P, or whatever, and then through A prime, B, P.
You need a plane.
Huh?
You said point.
Oh, sorry. Basically construct those planes
That meet at a line.
that intersect at a line, pick another point on that line, and then there we go. That's how we're going to get our other line,
That's such a weird.
because it's going to be equidistant from both A and A prime.
And then you get your.
And then that gives us our other point to construct our other line, and then with 2 lines, that gives us our perpendicular plane.
Okay.
So that's how we get a plane, and then how do we know that it's one and only one plane? Well, because once you have the 3 points, you're guaranteed that that's a unique plane.
And how do we know it's perpendicular? That plane we constructed.
The equidistant from A.
You pick the point equidistant from A and A prime.
Because AP and A.
Does that
Yeah, I
necessarily-
just said that, but let's think about that
Does
for a
that
second.
necessarily guarantee that it's perpendicular though?
Yes, if it's equidistant from A and A prime, it's for sure perpendicular.
Yeah.
That's what it
If
meant to be. It meant that the line coming from P would be perpendicular to it, and that gives us our second line.
Right.
That's only if AP is congruent to A prime B, right?
B, which is Right. Yeah.
Yes. Picking A so that this is congruent to that.
Then anything
By
equidistant
choice.
is going to be on
Then
the
any
plane
point
of A.
equidistant from A and A prime is going to be on a line perpendicular to L through the point P. It's going to be on a perpendicular bisector through that line. Segment.
Yeah.
That makes sense?
Yeah.
So basically, the previous proof following it gives us a construction for how we find the plane. And then the next one I think he said after that is now, what about for a line L and a point P not on the plane? Well, we already know how to construct the perpendicular to this to get the point P prime, and then it's just repeating the same problem as before. Make sense? In other words, we would still pick the point A here and the point A prime here. So that this distance was congruent to this distance. So whatever that segment is, find that same segment over here. There you go. Once you've got that, you're guaranteed. Drop its base. The plane through here is also going to contain that point, since it's on the perpendicular bisector. And that's going to be the one and only one plane that we had from the previous problem. So if I give you a line, just try and show you it in three-dimensional space, a line and a point not on the line at the top of this chalk here, there's one and only one plane you can do through the tip of this chalk that's also perpendicular to that line there. If this line happens to be sloped like this, here's L, here's our piece of chalk. There's one and only one plane I can construct through the top of this piece of chalk such that it's also perpendicular to that line.
Yeah.
That's what we're saying, trying to get you intuition for it in three-dimensional space. Okay,
Can I grab some water?
sure. Next one, if two lines are perpendicular to the same plane, they are parallel. So I've got two lines perpendicular to the same plane, L and L prime. Then they're also parallel to each other. Seems like we need a definition before we talk about lines being parallel to each other. I think I must have missed a definition.
Doesn't being parallel just mean they have no intersection?
No, so let's really quick talk about what it means for two lines to be parallel. First, let's talk about what it means for two lines to be skew. Let's take this line that goes through these 2 points, and now let's take the line that starts right here. Here's a point out of the blackboard. Here's a point sticking out of the blackboard. Here's another point. Let's look at the line that goes through this point and goes into the blackboard right here. And then it goes out forever. So one line lies completely in this plane. This one comes out of the blackboard right there and goes shooting out of the blackboard forever. And here it intersects the blackboard going in forever. Notice that those two lines never intersect. Or to give you a more concrete version, take the line at the bottom of this classroom, extend it to infinity, and take the line at that top corner of the classroom and extend it to infinity. Those two lines never intersect. Are they parallel?
Yeah, because parallel means that it's just two lines that don't intersect.
That's what parallel meant inside of a plane. But intuitively, is that what we mean by parallel? Is the line at the top of the classroom over there, this parallel to the line at the bottom of the classroom right here? No. What does it mean, explain it to a sixth grader, for lines to be parallel? They're like going in the same direction somehow, right?
Yeah.
Two lines that point in the same direction are parallel lines. So these two lines are just called skew lines. Skew lines are lines that do not intersect. So we can no longer use as our definition of lines being parallel that they do not intersect.
In this geometry, we can't use that as the definition of parallel.
Yeah, in this geometry, we can't use that as our definition of parallel. Those are just skew lines. So what does it mean now for two lines to be parallel? And we kind of want to piggyback on our previous definition. So think about how in our new geometry could two lines be parallel. We don't just want to capture skew lines, so the line at the bottom of this classroom and in that top corner are not parallel, even though they never intersect.
If they're
Yeah, but we're thinking like
perpendicular
these
to
two
the same
top
plane.
corners would be parallel.
Right, but the lines at the top and the bottom of this wall right here, we want them in some sense to be parallel. What's a property that the lines at the top and bottom of this wall have that the line at the top of this wall and the bottom of that wall don't have?
What's the word?
You're like they're going in the
A
same
transversal would.
They're going in the same direction. Notice that we're also both on this wall.
You're in the same
Oh,
plane.
yeah.
They're in the same plane. There we go.
Same plane.
So two lines are parallel if they're coplanar and they don't intersect.
That makes sense.
And if two lines don't intersect at all, then they're just called skew lines. So that is different from being parallel. So I'll read his exact definition here now. Two lines are called skew if they do not lie in one plane. Now, if they don't lie in one plane, they can't intersect. Because any two lines that intersect can lie in the same plane. Take any two lines that intersect in space, we already proved that there's one and only one plane that contains those two lines.
Yeah.
So, if two lines are not even coplanar, it's impossible to stick them in one plane. That's what we mean by skew. So, one, they don't intersect, and two, they can't lie in the same plane. So, skew is different from parallel lines. Question, are parallel lines skew? Since they never intersect.
Because
No,
they're on the
they
same
lie.
plane.
No, because they're coplanar and never intersect. So if they're not even coplanar, they're skew. Coplanar, it's impossible to intersect. That's more than that. It's impossible to stick them in the same plane. That's what skew is. Parallel is, you can stick them in the same plane, but they still don't intersect. Make sense? The difference there? Okay. Theorem 10.4. Through a point P not in a plane pi, there is exactly one plane parallel to pi. So, in other words, let's think about this wall. Here's the plane. What we're saying now is pick any other point in space you want. There's one and only one plane you can construct through that point parallel to this wall. Make sense? From here on out, just making sure you understand what the theorems are saying and giving you intuition for the theorems. We're going to stop trying to draw these pictures. Theorem 14.11. Two planes perpendicular to the same line are parallel to each other. So think about the wall at the front of this classroom and the wall at the back of this classroom. Now construct the line perpendicular to this plane. So it comes out of it perfectly at a 90-degree angle. Then it's also going to stick into the back wall perfectly at a 90-degree angle if the two walls are perfectly parallel. That's what it's saying.
Are you saying planes are...
If a
parallel?
line is perpendicular to two planes, then those planes have to be parallel, and vice versa. Let's read exactly what it says. It says two planes perpendicular to the same line are parallel. That's what it says. So if two planes are perpendicular to the same line, then those two planes are going to be parallel. And how could you intuitively quickly see that? Looking on it perfectly from the side, here's our wall. Looking on it perfectly from the other side, here's our wall. Now let's look at the line that I know is perpendicular to both of them. Well, if we capture the plane that I've drawn here, then obviously this line is going to be parallel to this line.
Yeah.
And those two planes will never intersect.
Yeah.
Yeah, but they'll never intersect with the
Pick any line in this plane and any line in this plane. Any two coplanar lines, and those two lines would never intersect. And only coplanar lines could
Are they
intersect.
also skewed?
No. Planes now, I don't know if he even said it. What does it mean for two planes to be parallel? They never intersect.
He says that.
Okay,
Part of
but that's
that
what
is
the definition of skew
14.
was, wasn't it?
Okay, so I skipped that part of definition 14.1. Sorry.
Oh.
Or definition 4. Two planes are parallel if they never intersect. So that used to be what it meant for two lines to be parallel in two-dimensional space. They never intersect. In three-dimensional space, two planes are parallel if they never intersect. If we upgrade to four-dimensional space, then two three-dimensional spaces are parallel if they never intersect. And you can keep generalizing to higher and higher spaces. So two planes are parallel if and only if they don't intersect.
Yep.
Yeah.
Make sense? Okay. Theorem 14.2. If two lines are cut by three parallel planes, the intercepted segments have lengths that are proportional. Okay. Here's what he's saying. We already proved the theorem just like this.
Yeah, here, man.
We are looking from a bird's eye view down on some constructed walls. So, looking down on a bird's eye view, someone went along and they built this wall, and they went along and they built this wall, and they went along and they built this wall. All those walls being parallel to each other, bird's eye view looking down at it. If I were to now come with some line and cut it like this and like this, and I cut it so that this is the same as this, then this is going to be cut the same way as that. For planes. However, they are proportionally cut this way, they're also proportionally cut that way. So we prove that with lines. That is also the case with planes. Or, whatever ratio you cut this at is the same. So in general, what he's saying is if we call this A, B, C, A prime, B prime, C prime, I think that's his exact labeling, A, B, C, and A prime, B prime, C prime, then the length of AB, which way does he decide to give it? AB over A prime, B prime. The ratio of this to this is the same as the ratio of that to that. AB over A prime, B prime is equal to BC over B prime, C prime. Or, the way I would have thought about it is the ratio of this to this is the same as the ratio of this to this, which is the same algebra here, you just swap those two.
Yeah.
Divide top and bottom by BC, multiply top and bottom by A prime, B prime. That's the way I would have thought about it, but just be consistent with the way he gives it. And then, we're ready for our definition now of a polyhedral angle. We already went over a dihedral angle. A dihedral angle was kind of the angle you get when you intersect two surfaces. A polyhedral angle is going to be multiple surfaces now intersecting. So it's our more general way that we can create an angle. Give you an example really quick of a polyhedral angle. Think about the angle in the top of our classroom there. So the angle in the top of our classroom there, it's like these 3 points coming together at that corner. And that creates a sort of 90-degree-ish angle, in a sense. So that's going to be an example of a polyhedral angle. So what is it more generally? More generally, we'll just go over his exact definition rather than me writing it out. Let P1, P2, Pn be a simple closed polygon in plane pi. What is a simple closed polygon? It means that there are a bunch of segments that ultimately close on each other. So draw the picture for what he's talking about over here so that you can understand it. So here's P1, P2, all the way up to Pn. So dot, dot, dot. Could have arbitrarily many, but in this case, just drew 5 points. So let P1, P2 be a simple closed polygon in plane pi, and let V be a point not in pi. So V now is going to be like the actual corner of that classroom. So V is going to be some point that sticks out of the whiteboard here. And we're going to be using that to construct our angle. So it's going to be like the vertex of our angle. So he called it V, right? V, obviously, for a vertex, put a circle around it to remind you that's sticking out of the whiteboard. It's out here some distance. Okay. The set of points Q on rays from V through all points P of the polygon is called the polyhedral angle. In other words, let us, I wish I had like surface stuff to use. I don't know if that's going to help any. So I've got my point V actually sticking out of the board now, right? Now construct a ray from my vertice to this point, to this point, to this point, to this point. All infinitely many rays. And it's creating this closed shape.
Like a cone?
Like a cone-ish type shape, but with this ugly bottom rather than a perfectly circular bottom. But I think you got the right idea. Now extend that to infinity. That's your polyhedral angle.
Oh, gross.
Rather than just an angle like in two-dimensional space. Remember, an angle in two-dimensional space is like that. Pick any two rays out of this thing and they kind of give you one of those. So it's an infinite number of rays starting at some point, shooting through every point in this polygonal path, creating this solid surface. Kind of like a cone, but with this ugly, jagged, bottom-looking thing. But the cone goes on to infinity. Think you got intuition for it? And so you can see how the top corner of the classroom is a polyhedral angle, assuming that the walls and ceilings go on forever. Okay. So we call V the vertex. And then we call V to P1 and to P2 to these actual points in our polygonal path. We call those the edges. So again, in our top corner there, the edges are exactly what you would have guessed. I said, look at the three edges of that corner. Look at the three edges of that angle. It's exactly what you would have guessed I was talking about. So that's exactly what the edges are. The edges are the rays, V to P1, V to P2, V to P3, dot, 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 V to Pn. How many edges does this one have? This concrete one that I drew? 5 edges, right? How many rays would it take to construct the entire polyhedral angle? An infinite number. Just make sure you're not thinking that it's just those 5 rays that make up the angle. There's infinitely many rays, it's just those ones are the edges. Because the whole thing's filled in. It's solid. It's an entire surface. Make sense? Okay. The planes, V, P1, P2, V, P2, P3, da 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 da, we call the faces. So think about the plane now. It has V, P1, and P2. That plane, as it cuts through, it gives me that face of it. How many faces does a corner in the top classroom have? 3 faces. This face, that face, and the top face. That's exactly what we mean by the faces here. Pick a point on one edge, a point on another edge, a point on looking at this wall, pick a point on that edge, which means from the top corner, and pick a point on that edge, which means a point on that edge. And then the vertice, those 3 points perfectly give me this wall. This wall is a unique wall that contains those 3 points. So, if you pick a point using the vertice, and then P1 and P2, that perfectly gives you the plane through V and those 3 points. And then if I repeat, use V, P2, P3, that perfectly gives me the plane through those points. And then through those, through those, through those. So, it has 5 edges, and it has 5 faces. So those ones are called the faces of the angles. And then the polyhedral angle is called convex if the polygon P1 through Pn is convex. This one is a convex shape. Let me give you an example of a shape that is not convex, just as a reminder. Here's an example of a shape that is not convex. So if I would have used that, make my vertex right here V. That point comes out of the whiteboard, and then we go through all those. Now that's really much harder to picture for us, right? That would not be a convex polyhedral angle. This is a convex one. We like convex ones, they behave nicely. Really quick, what did it mean for this shape to be convex? Intuitively, what's ugly about this shape? What's nice about this one?
The indenting.
It indents in some sense. Intuitively, what it means is that any segment, if your shape is convex, any segment from one side to another side never intersects the shape. Over here, notice if I construct a segment from this side to this side, it intersects the shape. So if none of those segments connecting 2 sides intersect the shape, then the shape is convex. Here's one that's not convex. Quick refresher on that. Good so far? Okay. The sum of 2 faces the sum of two face angles of a trihedral angle is greater than the third face of the angle. So a trihedral angle, now, what's a trihedral angle?
An angle 3 sides.
An angle that has three.
Or 3 faces.
3 faces or 3 edges, however you want to think about it. So we start out with our polygonal chain. P1, P2, P3, and then our vertex, V, sticking out of the board. Now I know from the triangle inequality that 2 sides are always longer than the remaining side. Right? And each of those triangles, once I construct it to the vertex, you can kind of see how they pretty much have the same height, so to speak.
Yeah.
And so since the base of this one and the base of this one, they're not quite the same height.
Yeah.
This is just intuition. I don't know how to give you a good taste for this. You could draw out the heights, but again, you would want analytic geometry to do that, to talk about the equation of its height for each point, and coordinates to do it. So I don't have an elegant way to show you this without some analytic geometry.
Really? There's no way to do it with what we already have.
There's always a way to do it. The question is, how much is it a pain and what's the payoff for how it could have been? Again, that's one of the major reasons we don't bother diving that much into these things. Talking about where a line intersects a plane is real easy to do when you have the equation of the line and the equation of the plane. That's trivial. It's much, much harder to just say, I've got this line and this plane, and how do I justify that they even intersect? And you have to think and kind of be clever, whereas with analytic geometry, you just check, do they intersect? Is there a set of equations that satisfies both? The same way you check, do 2 lines intersect? So, there's always a way. But it's just, I don't know. It jumps a little bit to what we'll be doing next week is analytic geometry. In analytic geometry, the guy most credited with developing analytic geometry is René Descartes.
Yeah.
And one of the reasons he developed analytic geometry is because of how tedious it was trying to come up with proofs in geometry. How you always have to be clever over and over again. But so all this is saying is that the sum of 2 faces, when you're talking about its area, is always bigger than the other face's area. I can't construct a trihedral angle so that one of my faces is bigger than the sum of the other 2 faces.
Okay.
I mean, there could be an elegant way to do that. By minimizing it, I could say that the face of this thing is always greater than if I just gave it the height from here, from the base to that, and then somehow use lower bounds on it. Maybe a way to do it that way. I don't know, I'd have to think about it. Okay, a polyhedral cell. What is a polyhedral cell?
We have to do exercise 14A.
14a. With scotch tape and cardboard, construct a number of polyhedra. No, you do not need to do that. Okay, a polyhedral cell.
It's on the syllabus, guys.
In the set of points, it's the set of points on or interior to a simple plane polygon. And then we call the edges exactly how you know how to call the edges. In other words, when we talk about a square, we are only talking about the actual segment here. If I want to refer to the point, this thing, that is now called a cell. So a polygon is just the edges, and then a polygonal cell includes the interior. It's like the difference between a circle and a disc. Circle, just the edge, disc, including all the points in between. All right, theorem 14-15, a polyhedron separates space in the following sense. How is a polyhedron going to separate space? You're going to have all the points inside it and all the points outside it. That's how he's going to explain this. But you already have intuition for it. Think about this top angle of our classroom once again with these walls going off to infinity. So no back walls. Now you have everyone inside that shape and then everything outside that shape. And so it separates space in that sense. So that's what he's saying here. A polyhedron separates space in the following sense. The points not in the polyhedron consist of two sets called the inside and the outside, such that a polygonal path joining a point and an outside point must intersect the polyhedron. So 2 points are outside if they somehow intersect the thing, and then they're both on the inside or outside if that's not necessarily the case. By a polygonal path, not necessarily just a strict segment. Let's get a concrete example really quick. Think about a simple polyhedral would be like inside this classroom. So here we are inside this classroom. Polyhedron, some three-dimensional shape. Think about your different dice, for example, of polyhedron. Something just composed of a finite number of polygonal cells. Everything is either inside this classroom or outside this classroom. Now, from a bird's eye view, looking at this classroom, assuming it's a rectangle for a second, 2 points are inside the classroom. If there is some polygonal path we can construct connecting the 2 points that doesn't intersect this. 2 points are outside the classroom if there's a polygonal path we can find connecting the 2 points that don't intersect the classroom. Inside versus outside. So rather than it being a segment joining them, it's some sort of polygonal path joining them. If there's some path you could take to get to John right now without intersecting this classroom, so going through the door, then John must be inside this classroom with you. If there's a path you can take without leaving the classroom to get to John, then John is inside the classroom. Similarly, if there's a path you can take to get to John, and you start outside the classroom, without intersecting the classroom, then John must have also been outside the classroom. Okay. The area of a polyhedron is exactly what you think of is. It's the sum of the areas of the face. Now, our formulas for volume. And this will be the last thing we talk about, just to introduce you to these formulas. First off, how do we find the volume of some rectangular prism?
Length times width and height.
It's just length times width times height. So we've got some prism here, length, width, height. What is the volume? It is simply the length times the width times the height. Exactly the way you know and love. For any parallelepiped, what is a parallelepiped? It's something where all the edges are, in some sense, parallel to each other.
Oh, like a quadrilateral?
So, I'm trying to draw it so that the face is flat here. So that face is flat, these two faces are parallel to each other, and all those are parallel to each other. And how do you get the height? Once again, you get the height of the thing like that, and then it's still just the area of the base times the height.
Yep.
So it doesn't matter if you skew it or you hold it straight up. It's kind of like how it follows from the fact that a shape like that has the exact same area as a shape like this. It doesn't matter that it slants over some.
Yeah.
As long as they have the same base and the same height, they have the same area. So again, the volume of that thing is still just length times width times height, or area of the base times the height. Same type of thing. The volume, we already did that. The volume of a prism is general, is equal to the area of the base times the altitude. Any prism is basically going, the edges are going to be straight, so to speak, smooth. And they all flow with each other. Finally, well, not quite finally now, the volume of a, pyramid, is going to be 1/3 the base times the height.
Yeah.
So now, notice the edges are not all parallel to each other. They're in some sense slanting on each other. So we can no longer use just area of the base times the height to get the thing. So once the edges start slanting in some sense, now you have to rethink it. In the case of a pyramid, it comes out to 1/3 the base times the height. That would be a simple proof in calculus. I think we already did that one in calculus.
Yeah, we did.
So again, that's something simple to prove once you have calculus. So we never go through the pains here.
I think we stop at exercise group 4 and 50.
yeah, so we won't go beyond these, but we're just basically going to finish up the formulas. What's the formula for the area of, or for the volume of a cone? If I've got a cone here,
It's gotta be 1/3 of the volume of cylinder.
we've got some cone with a height h. Again, it's similar to what it is for a pyramid. A pyramid, it was 1/3 the area of the base times the height. A cone is the exact same thing. It's 1/3. What's the area of a circle?
Pi
Pi r squared. The area of the base times the height. And so that also gives you the volume of a cone. Same concept. I think we skipped surface area of a sphere. The surface area of a sphere, you've probably come across before.
Whoa, that's kind of a bit advanced, isn't it?
Surface area of a sphere. So the area that goes over the surface. What's the surface area of a sphere if it has radius r? It is 4 pi r squared.
Oh, yeah.
It's the same as 4 circles of the same radius.
Yep.
Now, we won't prove this once again, but the way that the proof works, the hard part of it, is there is a way of projecting
Onto a cylinder?
onto a cylinder of the exact same radius, of radius r, that wraps around it. And it turns out that a sphere projected onto that cylinder, there's a way of projecting it so it has the exact same area. And then the area of the cylinder is, notice without the top, just a part of the cylinder that wraps around. So if I unwrap that cylinder containing the sphere, so there it is unwound, what is the height of the cylinder?
R.
2r. Radius gets us halfway.
Oh yeah.
So it's 2r here, and then the length of this part is the circumference of the sphere, right?
2 pi r.
Which is 2 pi r. And now you multiply those together, and what do you get? 4 pi r. And the way that you can relate this to a circle, if you remember when we briefly talked about how we get the area of a circle, the way we do it, if that's r, I kind of think about splitting this up into a bunch of little triangles, right? And then when you add up the base of all those triangles, then it's going to be the circumference 2 pi r,
Is it
and the
not?
height of each triangle is basically r. Go ahead.
Oh, I was gonna say, is it not 2 pi r squared?
For a circle. For a circle. Yeah, so we think about splitting up the bases into a bunch of different pieces. Adding up all the bases of all those triangles is 2 pi r times the height r, but it's 1/2 the base times the height. So 1/2 the base of all those triangles added up times the height gives us pi r squared. Or in other words, the area of that circle right there is the same thing you would get if you drew the triangle. So that this is 2 pi r, and this is r. Or if you drew it, doesn't matter how you drew it, you could draw it slanted like this. And it's the same thing. And now you can see how this easily divides up into 4 of those triangles.
Okay, that makes sense.
And then the volume of a sphere, no reasons for you to know this, but 4/3 pi r cubed, and those are just, you kind of just have to memorize these things. Again, these things are easy to prove with calculus,
Yeah.
but you need the calculus. And it turns out they're very, very easy with calculus. Outside of that, pretty difficult. Good? So again, I know that was a lot. Thinking about these things in 3 dimensions, that's a pain. But the homework will be much, much easier. And you do not need to do any of the constructions on the homework. Okay? Any questions? That went longer than I intended. I thought that'd be quick. We dived into the proofs a lot more than the author did.
Can we use geometrical reasoning to do proofs higher than the 3rd dimension? Like how we're doing these proofs without any analytic geometry, is that possible?
Oh, yes, it would be possible. I don't know anyone crazy enough to do it. You would just use analytic geometry. Everything, generalizing in analytic geometry is shockingly easy.
Yeah.
Going from 2 to 3 dimensions introduces a few problems, but then going from 3 to 4, 4 to 5, 5 to 6, It becomes easy.
What would be like an example of a proof that you would do in 4 dimensions?
So for example, the distance between 2 points in 3 dimensions, you've probably already come across before. That is the square root of x2 minus x1 squared plus y2 minus y1 squared. There it is in 2 dimensions. In 3 dimensions, it's just plus z1 minus z2 squared. And if we went to even more dimensions, then it would also be plus w2 minus w1 squared. Oops, should put the 2 there and the 1 there. And it just generalizes to however many dimensions you want.
Right.
So there's one that, when you prove it in the 2-dimensional case,
You prove for all.
the proofs going further isn't much more difficult.
Is that something we did in topology?
Yes, we may have done this in topology. I don't remember off the top of my head whether or not we did. And you could do proof by induction to show that it works for any n number of things that you want.
What would be a geometric proof in the 4th dimension that you could do?
So you could again try and prove the Pythagorean theorem in 4 dimensions. Notice that this gives you the results of the Pythagorean theorem.
Yeah.
It encodes the results somehow. And so this is really simple. Coming up with a 4-dimensional version of the Pythagorean theorem or a 3-dimensional version of the Pythagorean theorem, it just gets messier. Now you could still do it. The way you prove it in 3 dimensions is you break up your triangle into a bunch of 2-dimensional triangles. So when I talk about, we're going to get in trouble here trying to draw pictures. So here's my axis. There's my axis. We got the same, and I want to talk about the distance from here to here. Geometrically speaking, how I would prove the Pythagorean theorem is I would work with, rather than working with the distance from here to here directly, first I would work with the distance from here to here, and then the distance from here to here. And then that would be the triangle I would use.
I see.
So first I show it holds for the distance from here to here in the back plane. And then this distance is just that distance, and then I work with it again using this triangle in this new plane.
And you could do the same.
And if you did it in 4 dimensions, it would be a similar thing where you break it down into its 3-dimensional versions, into its 2-dimensional versions, do it with its 2-dimensional versions. And the problem is we rely so much on pictures for geometric proofs. And trying to picture those things is now just broken. So it's pain, nobody does it.
Has it?
And once you're talking about the equations of it, oh my goodness, who cares if you add an extra W? Working with vectors that contain 3 things in them instead of 4 things, or 4 instead of 3, it's trivial. So once you have vector calculus and you think about those as vectors,
It's easy.
it's much easier, yeah. That's what you learn in linear algebra is working with 3 dimensions and 100 dimensions,
Same thing.
same thing, it's just a lot longer to do the computations if you're doing it by hand.
Okay.
Okay, anything else? Okay, so we'll do analytic geometry next week, and that's the last chapter of the book.
Well, no,